So the main result we've had so far was the theorem that said that a distance matrix D is Euclidean if and only if its corresponding centered inner product matrix B, which was -1/2 H, D had a product with D, H. So D is Euclidean if and only if B is semi-positive definite. And in that case, we said that the data matrix X, which is given by U lambda to the half, has distance matrix D. Okay, so that's the thing we had so far. Now, often we'll be given a distance matrix D that isn't Euclidean, or maybe not quite Euclidean. Yeah, maybe our points have been recorded with error. Yeah, maybe there's a measurement error process going on. Or maybe there just isn't a Euclidean configuration at all. Now the theorem can still be useful, what we did before. So if D is non-Euclidean, let's say, if D not Euclidean, B is not positive definite, or it's not positive semi-definite. But we can consider the positive part. We can consider the positive part of B. Okay, so let's consider the spectral decomposition of B. So we can write B, we know, as the sum from I equals 1 up to K, its rank, of lambda I, UI, UI transposed, where lambda I are the eigenvalues, UI are the eigenvectors. Okay. So we're going to have lambda K is less than 0 if B is not positive definite. Yeah, not positive semi-definite. There must be a negative eigenvalue somewhere. The positive definite part of B is, let's call it B pos. So we're just going to sum up all those i's such that the eigenvalues are positive. So we're going to have exactly the same form as before, lambda I, UI, UI transposed, but we're only going to take the positive eigenvalues. So then B pos is positive semi-definite. So now once we've got B pos, we can use the theorem we had before. Okay. X, which has a distance matrix B pos with corresponding inner product matrix B pos. Okay, so if we're given a non-Euclidean distance matrix D, what we can do is we can consider its centered inner product matrix B, and then B won't be positive semi-definite, but we can construct the positive semi-definite part of B, and then we can apply the theorem to that positive semi-definite part, and then we can get a set of points X here that have a distance matrix D pos, a Euclidean distance matrix D pos with that does have inner product matrix B pos. And let's just say if the negative eigenvalues are small, the negative eigenvalues of B are small, then B pos might approximately equal B, and D pos might approximately equal the original distance matrix D. Okay, so let's look at an example. Okay, so as our example, we will take the distance matrix we had before, but we're now just going to change two of the elements. So I've changed this element here and this element here to be 0.5. So we've no longer created these points as Euclidean distances. I've just changed this number on a whim. Okay, so let's see what happens when we do that. Well, let's do what we need to do. So let's let A be minus a half times D2 squared, the Hadamard product of D2. And then we're going to let B2 be H times A times H. Okay, so it gives us a matrix of inner products. Now let's look at the eigen decomposition of B2. Whereas before, the eigenvalues we found of the centered inner product matrix were 2, 2, and then all the rest were zeros. Whereas now we've got something that's slightly bigger than 2, 2, something that's small, about 0.1, a 0, and then we've got a negative eigenvalue. So this matrix is not positive definite. Okay, this matrix is not positive definite. It's got a negative eigenvalue. So by the theorem, we know that this is not a Euclidean matrix. There is no set of 5 points in any RP space that has Euclidean distances given by the matrix D2 here. Yeah, it's not possible to find those points. But what we can do instead is find the positive part of B. So if we let lambda be the diagonal matrix that is formed, so let's call this lambda square root, the diagonal matrix of the first two eigenvectors, eigenvalues square rooted. Okay, let's just check that. Yeah, so diagonal matrix with the square root of 2 or close to square root of 2 on its diagonals. And let's let U be the first two eigenvectors of B2. Then we can create a set of points that is U times square root of lambda. And so this is a set of points. If we look at its distance matrix, Y, this distance matrix is an approximation of the distance matrix we had originally. So let's do this D. Okay. So the distances are different, quite different in places. Oh, that's not the right distance matrix, is it? Okay, sorry, distance X. Yeah, so distances are different here. So 0.83 versus 1, 1.016 versus 1, okay, 1.42. But you can see that they're close. We've found a set of points that has approximately got distances equal to the distances we started with. And we did that by using the positive part here. Here, I just used the first two eigenvalues, but I could do it with 3 eigenvalues. So let's do that, see if we get closer. So U could be the first 3 columns here. The square root of lambda can be the first 3 eigenvalues. Let's now let Y be, I'm going to call this Y2, be U times lambda. So let's look at these. So these are now points in 3-dimensional space. And let's look at their distance matrix. Okay, compare it with this matrix of X. And you can see we're slightly closer than we were before. It's a slight improvement, not much of an improvement, but we're slightly closer to this distance matrix. We're pointing in 3-dimensional space. So as always, there's an R command. So if we do CMD scale, classical multidimensional scaling, we apply it to the matrix D2, and we get to specify here the points. Okay, so the dimension of the point. So if I specify dimension 2 here, we get this set of points returned to us. So let's look at the distance matrix here. And this is the same, I hope, yep, as the distances of the y's we computed ourselves. So there might not be the same points. If we look at y, in this case, it has given us the same set of points. Look, yeah. Yes, the same set of points. The output from CMD scale is the same as the output we computed. Yeah. There's some rounding issues, but you can see it's the same set of points, and the distance is exactly the same. Or we could specify here that we want a set of points in 3 dimensions. Okay, so we get this set of points. So again, let's look at what we called distance y2. And you can see we've got the same distances. And if we look at the point cloud, they might be the same as well. Yes. Okay, so these are the same set of points. So what we've done here, we've taken a data matrix, and we found that it is not a Euclidean data matrix because it's in a product matrix. B was not positive definite. So we then considered the positive definite part of B, found a new set of coordinates from the positive definite, from the positive eigenvalues only, and we use these to represent the distances here. Okay. And if we plot these in 2 dimensions, if we take these 2-dimensional points, we get a set of points that is approximately similar to what we had before. But we know it can't be exactly the same because there is no set of points that will exactly give us a distance matrix D2. Okay, so these points here look like the points we had before, but the distances are slightly off. It's an approximation. Okay.